Okay, 2.2 is the motion of charged particles inside electric fields. So we know that electric fields can be created between two parallel plates, like this one here, one on top and one on the bottom. Now, the one on top, let's say this one is positively charged, and the one on the bottom is negatively charged. Oops. Yeah, you get the point. And we can say we shoot a proton, a positive proton, into this area into this area that has a uniform electric field. Now, tracing back to yesterday's video, Unit 2.1, we know that the electric field for proton would be something like this. The lines going from top to bottom with the arrow pointing to the negative plate. And this is because we are imagining that when a proton is placed in this area, it will accelerate toward the negative plate. And that's what will happen for this proton. Say we just eject this proton horizontally with no initial vertical velocity. It is going to act like projectile motion. It's going to be like attracted to the negative plate. And the calculation for that is exactly the same for projectile motion, which we did in term one. So usually in a question like this, we're given the strength of the electric field between the two plates, and that's the E. And we also know the charge of a proton. That's on our equation sheet. It says the charge of a proton is 1.6 times 10 to the power of negative 19 coulombs. So to figure out the acceleration, what we do is we figure out the force first. So that's F equals E cubed. So F equals the electric field between the plates timing the charge of this proton. So that gives us the force. And using this force, we do F equals ma to get the acceleration. And then using the acceleration, we can do all sorts of calculation, like how long it takes to reach like max vertical displacement, all sorts of stuff. So this is motion of charged particle in between parallel plates. But you can also have, instead of having protons, you can have electrons. Now electrons are negative, they're not positive. So we know that negative repel negative and attracts positive. So the motion for this electron is going to be different. The arrows are going to be pointing this way instead of pointing down. Now let's get rid of everything on the screen because now we're going to talk about cyclotron. A cyclotron is basically a machine used to accelerate ions to an incredibly fast speed, and this ion is used to make radioisotopes. This can be used for treating cancer, for medicine, and other stuff. So, ion. Now, the essential parts to a cyclotron is really the two Ds, and also um, its own magnetic field. So two, one, two, and one, two. You get the point. So let's first look at the Ds. The Ds are basically like two hollow conductors. They're two hollow conductors. That means they have no charge inside them. but they have charge on the outside. And an ion source is in the middle of this cyclotron, so ions are being released into this device starting from the middle. And now another really important factor is the magnetic field. Now we see the x's on this diagram. That means the magnetic field is pointing into the screen. It's pointing into the screen because the arrow looks like this looks like an arrow. The tail of the arrow going away from our view. So that's would be a magnetic field going into the screen. Now let's say um, let's say we have a magnetic field going into the screen and this ions traveling horizontally. Now, using our right hand rule, we know that so our thumb is going to be parallel to the direction of the ion traveling, and our index finger on the other four fingers are going to be like making a slap. So your hand is going to look something like this. You know, that's your thumb, and that's your other four fingers, like that. Kind of like an oven mitt, but you know, the fingers, like that, like this. Thumb or like that. You know, you get the point. So your thumb is going to be parallel to the direction of traveling of this ion, and your fingers are going to be um, in the same direction of the magnetic field. So in this case, you're going to point your hand into the screen and your thumb to the right. And the direction that your palm is facing is the direction that the acceleration is the direction of the force that's being applied to this ion. So if you do this according to what I said, your palm should be facing upward. So the acceleration is upwards for the ion. Now the ion, because due to this acceleration, is going to change direction. It's going to change its direction of traveling. Now it's going to look like this. But when it switches direction and we do the same thing, if you just put your thumb parallel the with this arrow and point your other four fingers into the screen, you're going to see your palm facing left. So that means the acceleration is to the left now. Now this is very interesting because we see that the velocity and acceleration are 90 degrees to each other. And we learned the same thing in centripetal acceleration, that centripetal acceleration is always 90 degrees to the velocity. That's very interesting because we know because of this phenomenon that an ion traveling in this uniform magnetic field is going to make a circle. It's going to make circles. And another thing that is crucial to the cyclotron is the utilization of the electric field. Now we know that these are hollow conductors, so they have electric field between them. And scientists, the designers, designed this so it can accelerate the ion. How does it do that? Well, it does so through the electric field. So AC current, an alternating current is ran through this machine. So the electric field is alternating. We're going to draw lines like this, that, that, that. They're meant to be uniform. They're meant to be the same distance apart. And say we have an ion coming from this direction to the right, from the left to the right. At this stage, the electric field should be going this way, should be going to the right. So when it passes this gap between the D's, it's going to get accelerated because of the electric field. But when the ion is down here, going from the right D to the left D, when it passes this electric field in the middle, the current will have alternated. Thus, the electric field will be going this way. So now they're all going this way. And this process alternates. When it's up here, when the ion is up here, it will be in a way such that it accelerates the proton, the ion, in the right direction. So that's how a cyclotron works. And this is unit 2.2, electric field.